Hello, and welcome to another lecture on Cantera. In this lecture, we will learn about the Cantera input data files. The objective of this video is to provide an understanding of various sections of the input file without actually using them at this point. We will use these data files later. So earlier versions of Cantera data files were in the XML or the CTI format. However, the YAML format has now become the standard for all recent releases. So with that, let's go ahead and open a data file from Cantera database and go through the whole data file at once. So I will go to the folder where data files are saved. I hope you remember that from the previous video, but I will show that to you here as well. So here, if you see, let me, okay, so make it. All right, so here you go to the user directory, Anaconda, environments, environment names, lib folder, site packages, Cantera, and then you finally get to the data folder. Here, you will have all of these input data files. This is what we saw in the previous lecture. Let's just go ahead and open the air.yml file. This is a pretty simple input data file as compared to many others in this list. So I'll open the data file now. All right. So the input file here, it provides the elemental and molecular composition of air, along with the thermodynamic transport properties of individual species and the reaction mechanisms that follow. So the file begins with a general description. Here it tells us about the database, that this database is for ideal gas. It uses ideal gas properties and includes some reactions as well. Then the file goes on to mention the name of the generator. So this script, CK2YAML, is a script that is used that is used to generate data files. And we will actually generate our own data file in the future lectures. And you will see how to use this script to generate our own data files if you want to, or if you have to. Then it mentions the input files, which is air.inp and gri30 trans.dat. These are the files that were used as an input to this script to generate this particular data file, air.yaml. Then it mentions the Cantera version, which was used to generate the data file. And finally, the date when this input data file was generated. Next, the file mentions the keyword units, where it prescribes the units used for all relevant quantities. So for length, the file uses centimeters, time is seconds, quantity is mole, activation energy is calories per mole. Internally, actually, Cantera utilizes the SI units for calculations, but the units can actually be specified for individual quantities as well. Let me show you the units that can be used with Cantera. Let's go back to the presentation. Okay, so here are the different units that can be used for mass, length, time, temperature. So all of these are fundamental quantities, and then you have derived quantities as well. So with that, let's go back to the data file again and see the next sections of the data file. Then comes this part here. So the file then provides a name for the phase, and the name it gives for this entire phase that is described in this data file as air, which is to say that air is a combination of all of these species, and that actually constitutes a phase. Then the keyword thermo has been specified, and this is used to describe the thermodynamic model for this particular phase. In this case, we will be using the ideal gas law for all calculations. It then here the ideal gas model actually has been used, but there are actually several other models that are available, like constant density and Ridley-Kwong equation of state. I believe I have a list, or at least a link. Okay, so this link here can be used to see the different thermodynamic models that are available. Let's check out this link. So I will go to the browser and I will open this link and bring it to the screen. All right, so this is a part of the documentation of Cantera. And this actually gives you a lot of information here. This is where you see under the thermo category, you can see all the different equations of state that Cantera allows you to use. So let's go back to the data file again. Sorry, I have to switch back and forth quite a bit in this presentation, but all of that is needed just to explain the point clearly. Okay, so now a separate entry for kinetics is needed, which is here. So the species, actually, sorry, let's go to the elements and the species as well. So the elements in air will be oxygen, nitrogen, and argon. That is what this file states. And the species that form air will be all of these. O, O2, N, NO, NO2, N2O, N2, and argon. Now, a separate entry actually is needed for kinetics as well, which identifies the nature of reactions to be considered. Here, the data file specifies that any kinetics related info is for the gas phase. For a reacting flow system, actually transport properties like viscosity and thermal conductivity may also be needed. This is achieved by using a transport model, which is here. And this is defined as mixture average in this case. But the user may choose a transport model based on the level of accuracy and the computational complexity needed. Here, the data file uses a mixture average quantity, which is to say that it will be using different components of the mixture, but it will be using an average of all the components of the mixture. The properties will be averaged for all of the components together. But more sophisticated transport models are also available, and that is also, it can be seen in one of the links that I have in the presentation. So this is another link from the documentation in Cantera, where you can see all the transport models that are available. So let's copy this link and paste it in the browser to see what we have. All right, it's the same one. Okay, so here, transport. And these are the different models. So mixture average is the one that the data file uses, but you can have a multi-component unity Lewis number, etc. Again, I will not go into the details of the thermodynamic or the transport models, because that's beyond the scope of this course. That will be covered in a theoretical combustion series or a theoretical combustion lecture. This is mainly just about Cantera, so we'll just stick to the basic level. Now again, let's go back to the data file and see the later sections. So let me bring that up. Okay. Next section is this species part. This is a very important and a rather long sort of a section. And so you can see it says species here, and then it mentions the name O and the description goes all the way to line number 37, and then you have the name O2. So this is a separate description, which goes all the way to line 55, and then you have name N. So I'll go through this entire these segments rather. So here, the species part, it presents the atoms that constitute the species, the coefficients to calculate the specific heat capacities, enthalpy, entropy, and the transport data to calculate viscosity, thermal conductivity, and the diffusion coefficients. So you can see the name is specified as O, which means the O species that is here. So all of this detail is for the O species. And let's go back to the presentation, and we will talk about these details. All right, so I've just copied and pasted this the section that talks about the O species in the data file. So Cantera actually uses two polynomials to calculate the specific heat capacity, enthalpy, and entropy. One is the NASA 7 coefficient polynomial, the other is NASA 9 coefficient polynomial. And as you can see, the coefficients in NASA 7, they range from A0 to A6, which is 7 coefficients. And for NASA 9, they range from A0 to A8, that is 9 coefficients. And so by using these coefficients and these functions of temperature, we can calculate the specific heat capacity, enthalpy, and entropy of any of these species, right? And the 9 coefficient polynomial actually is the latest standard. This is the NASA 7 is the older version. The NASA 7 and the NASA 9 is the latest one. And you can also see a temperature range mentioned here, which is here. That tells the limits of temperature for which the polynomial curve fit was performed. So these are polynomial curve fits, and they were performed for a certain temperature range. In this case, we have two ranges. We have 200 to 1000 and then 1000 to 3500. So the data actually, or these properties, specific heat capacity, enthalpy, entropy, they were not able to have one single curve that could span the entire range. And so they divided the whole range into two curves. One is from 200 to 1000 Kelvin, the other is 1000 to 3500 Kelvin. And that is why, if you see, this data file, by the way, uses the NASA 7 polynomial, not the NASA 9. And so you will see here, there are two ranges. One is this particular range, or rather two sets of coefficients. This is the first set, and this below is the second set. And if you count, these are 7 coefficients for the first set and 7 coefficients for the second set. The first set corresponds to the first range of temperature, 200 to 1000 Kelvin. And the second coefficient set pertains to the second range of temperature, which is 1000 Kelvin to 3500 Kelvins. And so these are the two different curves that were used to plot the whole range of these properties. Then here, this link actually is pretty important. We can actually find the coefficients for many species that are not available in, say, Cantera input files, and you want to use them. And again, I'm not trying to go into too many details here, and we will exactly see how to construct an input data file, and then all of this will come together. But for now, all you have to know is that we can use this this website to find out many other coefficients that are not present in the Cantera input files. Let me just quickly show you this link. Let's copy it and paste it in the web browser. All right, so this is where we get to. If you click on the new NASA txt, these are the NASA 9 polynomials, and you have a lot more species here. So BI, BI plus, BICL, BICL2, all of these, if you see, have the polynomials mentioned. And when we go to the lecture on creating the data file ourselves, we will see how to use them. All right. And so the final section of the data file is what we will go through now. Let me bring that up again. So all of this is for species. All the different species have been covered here. Next section is on reactions. Finally, so this last section, the data file, provides the details about the reactions occurring in the system. And we will now look at the details of how does this happen, or what does this do. So this is a copy and paste of that section on reactions. This expression, you may be familiar, it is known as the Arrhenius rate expression. And these coefficients, or this data on reactions, is actually needed to calculate the gas phase Arrhenius rates for each reaction. So for the first reaction, for example, it says 2O plus M gives O2 plus M, right? This is a three-body reaction. So let's start with a simpler one, actually. So the second equation, N plus NO gives N2 plus O. This is reaction number 2, it says. The rate constant, it gives you the value for A, B, and EA, which is A, B, and EA, right? So that is how this data corresponds with the Arrhenius rate expression. And you will also see that some reactions have a different type, like three body and fall off, which is mentioned here, type three body, then type fall off. This again, without going into too many details, this should be covered in your theoretical lecture series on combustion fundamentals. But I'll still briefly tell you about it here. These are actually different types of reactions, which you will obviously study in your course. However, related to these reactions, you will see descriptions of coefficients are slightly different. In the three-body reaction, you have efficiencies coming up. And for the fall-off reaction, which is here, fall-off reaction, you have low pressure rate constant and high pressure rate constant. This is because in a three-body reaction, separate colliding species are needed. So in the three-body reaction, you can see there is this M, that's a colliding species. That's an extra species that actually comes in and stabilizes a sort of intermediate that is formed. And hence there is also a collision efficiency related to this reaction. And that is what you have here when it says efficiencies. Similarly, for a fall-off reaction, the order of the reaction actually depends on the pressure. And that is why you see a low pressure rate constant and a high pressure rate constant here, low pressure and a high pressure rate constant. Here actually are a few resources which have many other reaction mechanisms in them. So this reaction mechanism that you see was from air.yaml input data file. And this details any reactions that may happen inside the species that constitute air. If you want to look at any other reaction, say for methane, hydrogen, ethane, propane, butane, whatever other fuels if you need, there are other websites that are available. Or Cantera actually has many other data files for that. So let me quickly show you the other data files as well. We'll just go through the names actually. So air.yaml, then you have many other here. GRI, that is for methane. Then you have hydrogen peroxide reaction mechanism, KOH. So there you have quite a bit of information on reaction mechanisms anyways inside Cantera. However, if you do not have the reaction mechanism that you desire to use in your calculations, you can go to any of these websites and you may be able to find the needed reaction mechanism. So let me quickly go to one of these websites here. And let's see what they have. We'll just go to one. So paste. All right, so this is from Colorado State University, and there they have GRI-MEC. That's a reaction mechanism. They have Princeton University C1 hydrogen oxygen mechanism. These are the input files for this particular mechanism. And so this way you can go to each of these websites and you can find different reaction mechanisms. And I do encourage you to go and read the text that these websites have. It will certainly enhance your knowledge quite a bit. Now, we will actually learn about the reaction and how to use them in later sections. This was just a quick overview. But yeah, for this section, that was it on the input data files. So I'll see you in the next one. Thank you.